Hello, I'm Salim Valera, Chief Scientist at WaveOptics. We have designed and built a unique near-eye display with a small form factor but a large eye box. The small form factor has a number of advantages over conventional waveguides. For example, there are fewer interactions with the diffractive structures and therefore less scatter and a higher contrast in the image. The fewer interactions also mean that the waveguide tolerances on flatness and wedge are looser. The following animation shows the basic principles of how waveguides work. Conventional diffractive waveguides have three distinct regions of linear diffraction gratings. The WaveOptics waveguides, on the other hand, have just two distinct diffraction regions. The input grating, which couples an input pupil into a dielectric waveguide and sends it under TIR towards a low efficiency grating in conical mount. Part of the incoming pupil is diffracted or turned towards the third grating while the main pupil carries on undiffracted down the waveguide, producing a replicated pupil at each interaction. We call this process pupil replication, and this second grating thus replicates the pupil in one dimension. The array of replicated pupils head towards a third grating which partially diffracts the pupils out of the waveguide and towards the user. This third grating replicates the pupils in the second dimension, resulting in a small input pupil being expanded in two dimensions. The input grating, which couples an input pupil into a dielectric waveguide and sends it under TIR towards a low efficiency two-dimensional nanostructure region. Each interaction of the pupil with the nanostructure produces a number of pupils which spread in two dimensions through the waveguide and are also partially diffracted out of the waveguide towards the user. This results in a small initial input pupil being expanded in two dimensions. We now take a closer look at how the WaveOptics nanostructures work. We use a two-dimensional nanostructure with a certain periodicity and symmetry which maintains both angular and chromatic conjugation of each ray diffracted out of the waveguide with the ray incident on the input grating. These structures can be thought of as a combination of a set of two linear gratings, G1 and G2. The ray coupled into the waveguide by the input grating is incident on the nanostructured region. Part of the beam carries on undiffracted into the 0R component. Two symmetric turn orders also fork out from the interaction point, one caused by diffraction due to grating G1 and a second caused by diffraction due to G2. Both these orders are still under total internal reflection and continue onward to make further interactions with the second region. We follow one of these forks, caused by G1 component, along its path to totally internally reflect from the top surface of the waveguide and back towards the nanostructures for a second interaction. Three beams result from this interaction: the zero reflected order, a turn order due to G1 which is now turned back along the original path and is still under TIR, and a third order due to grating G2 which is no longer under TIR and is able to be viewed by the user. All the orders still under TIR go on to make further interactions with the nanostructures, producing a greater number of forks and fill in the eye box. We have thus managed to achieve 2D replication in the most ergonomic form factor. This animation has illustrated the unique design of the WaveOptics waveguide and the inherent advantages it offers. Thank you for watching.